Hi, my name is Geletu Qing. In this presentation, I would like to talk about our results on the electrochemical disinfection of irrigation water using low-cost graphite or titanium electrodes. This method is effective for disinfecting water containing low chloride concentrations by utilizing naturally occurring chloride ions. Therefore, chemical disinfectants are not necessary, and it also produces less toxic disinfection byproducts compared to the conventional methods using chlorine gas or hypochlorites. Foodborne diseases caused by pathogens are a significant public health burden. For example, there are about 48 million cases of foodborne illness and 3,000 deaths each year in the United States. And the associated expenditures on medical care and lost wages are more than $15.6 billion. And it is also causing the food industry billions of dollars in the recalls of tainted foods, lost sales, and legal expenses. Therefore, the FDA Food Safety Modernization Act, which went into effect in January 2016, aims to shift the focus of federal regulators from responding to contamination to preventing it. Importantly, the U.S. irrigated area reached 55.7 million acres. And irrigation water is the most important route of pathogenic contamination in fresh produce. Therefore, the disinfection irrigation water is a practical approach to preventing foodborne illness. Disinfection of irrigation water can be achieved by chemical or non-chemical methods. Most chemical disinfectants are hazardous to produce and transport, and their use also leads to the accumulation of chemical in the soil, water, and the irrigated plants. Hypochlorites and chlorine gas are the disinfectant of choice for most applications because they are highly efficient and also provide low cost. However, their use leads to the formation of toxic byproducts, for example, chloride and trihalomethanes. Ultraviolet irradiation is a non-chemical method. It is, however, sensitive to turbidity and it has no residual disinfection effect. Electrochemical techniques can enable the in-situ generation of disinfectants such as chlorine and hydrogen peroxide by utilizing naturally occurring ions and other species in water. It can also enable the direct electron transfer between the electrode and pathogens. Therefore, on-demand disinfection is possible, and it can also be powered with renewable electricity, which is very important for remote and off-grid farms. The first part of this presentation is the disinfection of irrigation water in Hawaii using a graphite electrode flow cell. The flow cell consists of two graphite plate electrodes placed in parallel, and water flows through the channel between them. The flow cell is connected to a bottle, and the water is circulated using a pump. This table shows the chemical composition of the two types of irrigation water, botwell pond and open ditch. The botwell pond water contains higher concentration of chloride, but it is less than 7 ppm. And the botwell pond water also contains higher concentration of ammonia, nitrogen, and total organic carbon. This slide shows the effect of current density and flow rate on the disinfection of botwell pond water. The flow cell was operated at open circuit for 60 minutes, and no disinfection was observed. In the first experiment, the red colonies on the plates correspond to coliform bacteria naturally occurring in the water, and it was completely disinfected after 10 minutes of treatment. In the following 3 experiments, E. coli was added, and it was disinfected after 20 minutes of treatment. However, the effect of current density on the disinfection efficiency was not quite clear, probably because the initial concentration of E. coli in the solution changed significantly. In the last experiment, there was a significant decrease in the disinfection efficiency, probably because at a higher flow rate, it became easier for the disinfectants produced at the electrodes to react with organic matter in the bulk solution in the bottle. This slide shows the effect of current density and flow rate on the disinfection of open ditch water. The results are similar, but the disinfection process is faster, most likely because the open ditch water contains a lower concentration of organic matter. Chlorine and hydrogen peroxide are the most possible disinfectants electrochemically generated at the electrodes. In the botwell pond water, the concentration of total chlorine increased with time, but free chlorine was not detected in the solution throughout the experiment. In the open-ditch water, the concentration of total chlorine also increased with time, and free chlorine was detected in the solution at the end of the experiment. Apparently, the high concentration of ammonia and organic matter in the Bothwell pond water consumed all free chlorine electrogenerated at the anode. Hydrogen peroxide was not detected in both experiments, and the concentration was confirmed to be significantly lower than 1 ppm. In addition, experiments in synthetic water without chloride showed negligible disinfection performance. These results demonstrate that the disinfection mechanism was controlled by chlorine species electrogenerated at the anode. To further confirm the role of free chlorine, a free chlorine solution was added to the Bothwell pond and open-ditch water. The free chlorine solution was prepared on-site by electrolyzing sodium chloride solution. The complete disinfection of the Bothwell pond water requires approximately 0.5 ppm of free chlorine, but the open-ditch water requires only 0.1 ppm of free chlorine. This difference is because the Bothwell pond water contains higher concentration of ammonia and organic matter. The disinfection effect of hydrogen peroxide was further examined by adding a commercial hydrogen peroxide solution to the Bothwell pond and open-ditch irrigation water. The complete disinfection of the Bothwell pond water requires approximately 200 ppm of hydrogen peroxide, and that of the open-ditch water requires approximately 50 ppm of hydrogen peroxide. Therefore, the disinfection effect of hydrogen peroxide during the electrochemical treatment should be negligible because the concentration did not exceed 1 ppm. The electrochemical disinfection of irrigation water using graphite electrodes provides several advantages. First, the graphite electrodes provide low cost. Second, the production and transportation of highly reactive chemical disinfectants are not necessary. Finally, the addition of other chemicals is also not needed. However, the graphite electrodes undergo corrosion during electrochemical treatment due to the electrochemical oxidation of carbon. Therefore, we perform the disinfection of open-ditch water using titanium electrodes. Titanium electrodes are well known for their high chemical and electrochemical stability. The experiments were performed in a batch cell assembled with titanium foils at both anode and cathode. Polarity reversing direct current was applied between the two electrodes to mitigate the formation of oxide on the electrode surface. In this work, the direction of the current was reversed every 5, 10, 30, or 60 seconds. This slide shows the effect of current density on the disinfection efficiency. The half period of the polarity reversing direct current was fixed at 30 seconds. The current density was first increased from 0.5 to 2, and then the experiment at 0.5 was repeated to confirm reproducibility. Finally, the experiment was performed at open circuit. No disinfection was observed at open circuit and when the current density was 0.5. When the current density increased from 1 to 2, there was a significant increase in the disinfection efficiency. The concentration of free chlorine and total chlorine in the solution was measured during the disinfection experiments. Free chlorine was not measured in the solution at all current densities. Total chlorine was not detected in the solution at open circuit or when the current density was 0.5. However, total chlorine was detected in the solution at higher current densities, and its concentration increased with both time and the applied current density. This slide shows the effect of the half period of the polarity reversing direct current on the disinfection efficiency. The current density was fixed at 2. The half period was varied from 5 seconds to 30 seconds, 10 seconds, and 60 seconds, and each experiment was repeated twice to confirm reproducibility. All experiments showed the near complete disinfection of E. coli after 10 minutes of treatment. However, the experiment at 10 seconds showed exceptionally promising result, achieving the complete disinfection of E. coli within 5 minutes. The concentration of free chlorine and total chlorine in the solution was measured during the disinfection experiments. Free chlorine was detected in the solution only when the half period of the polarity reversing direct current was 10 seconds, and its concentration increased from the first experiment to the second experiment. Total chlorine was measured in all experiments. However, its concentration at 10 seconds was higher than other experiments. The trends in the concentration of free chlorine and total chlorine matched very well with those of the disinfection performance. In addition, hydrogen peroxide was not detected in the solution at the best performing conditions. Therefore, the disinfection mechanism should be due to the formation of chlorine species at the titanium electrodes. The effect of chloride on the disinfection performance was further studied by performing disinfection experiments in synthetic water with or without magnesium chloride. Magnesium chloride is the sole source of chloride in the synthetic water. In another experiment, the magnesium chloride was replaced with magnesium sulfate to check the effect of magnesium ions on the disinfection performance. The results show that fast disinfection was achieved only when chloride was present in the synthetic water, and free chlorine and total chlorine were detected in the solution only when chloride was present in the solution. These results demonstrate that the fast disinfection was due to the generation of chlorine species from the oxidation of chloride ions at the titanium electrodes. An important question is why the titanium electrodes showed the highest disinfection performance when the half period of the polarity reversing direct current was 10 seconds. A possible reason is proposed based on the cell voltage data. When the half period was 5 seconds or 10 seconds, there was a fast increase in the cell voltage, which is probably related to the formation of an oxide layer on the electrode surface. At 10 seconds, there was a plateau after the initial increase in the cell voltage. It is expected that the titanium electrodes shows high activity toward chloride oxidation during this phase. When the half period was 30 seconds or 60 seconds, the cell voltage increased slowly in each half period. A possible reason is that when the direct current was applied for a longer time, a thick layer of oxide was formed on the electrode surface, and the resulting electrodes showed low activity toward chloride oxidation. The suitability of the titanium electrodes was examined by performing 30 tests at the best performing conditions. The odd-numbered experiments lasted about 10 minutes, while the even-numbered experiments lasted about 5 minutes. These results show that the complete disinfection of E. coli was achieved in each experiment. The cell voltage was also extremely stable during the 30 experiments, including the odd-numbered experiments lasting for 10 minutes and the even-numbered experiments lasting for 5 minutes. This slide shows the concentration of total chlorine after the 30 repeated experiments. The first 15 experiments were performed on the first day, while the other 15 experiments were performed on the second day. On each day, the 15 experiments were separated into 3 groups, with each group containing 5 experiments. The titanium electrodes were exposed to air for less than 10 minutes between experiments within each group, but it was exposed to air for approximately 45 minutes between different groups. This result shows that the concentration of total chlorine increased in each group. It indicates that titanium electrodes become more active toward chloride oxidation during repeated experiments. However, after exposing to air for approximately 45 minutes, the activity of the titanium electrodes returned to the original point. This result indicates that the titanium electrodes were oxidized by oxygen in the air and lost the highly active surface state. However, the highly active surface state can be restored by applying the polarity reversing direct current. The titanium electrodes provide multiple advantages, including low cost, no additional chemical disinfectants, no chemical addition, and high durability. The concentration of toxic disinfection byproducts was measured during the experiment. Chloride was not detected in the solution, and the upper limit was determined at 0.1 ppm. Bromo dichloromethane, dibromochloromethane, and bromoform were not detected in the solution. Chloroform was not detected at 5 minutes, and its concentration was 2.5 ppb at 10 minutes, and its concentration increased to 9 ppb at 20 minutes. However, these values are significantly lower than the recommendations for drinking water. As a conclusion, both graphite and titanium electrodes demonstrate disinfection of irrigation water, and the disinfection mechanism was controlled by chloride oxidation to chlorine. In addition, the titanium electrodes are expected to offer long-term stability. The electrochemical approach eliminates the addition of chemical disinfectants and also leads to the formation of low concentrations of toxic disinfection byproducts. We gratefully acknowledge financial support for this work from the Hawaii Farm Bureau and the Hawaii State Department of Agriculture. Thank you very much for your attention.